Well, number theory is obviously about numbers, and modern number theory, at least when it comes to the computational part, can no longer be done by hand because any kinds of numbers that human beings can wrap their minds around, we can now stick into a computer and check. And so if somebody wants to know whether a certain 200-digit number is a prime number, well, the only thing that helps there is large computers and large computer arithmetics. And that means that we also need to have a really good idea as to how numbers are represented within computers as well as in regular life. And we also need to have an idea how the various algorithms for addition, subtraction, multiplication, and division are implemented and how long they take. And so that's what this presentation does. So let's take a look. The underlying question here is, what is a number? And that question only sounds dumb before you think about it. Because really, what is a number? Good question, right? And there are quite a few questions like that. Think about it. You can probably drive yourself crazy with that. Well, numbers are used to represent quantities, right? I mean, 5 cows, 3 hungry cowboys, you do the math. But that does not say what numbers are, right? Because if you've got 5 cows in a meadow, that is not the number 5. That's still just 5 cows. Same goes with the 3 hungry cowboys. That's just 3 people. It's not the number 3. It's a representation. And so the construction of the number systems from set theory, which is a different course entirely, that gives a formal definition. But it's not what we want to work with on a daily basis, trust me. So this different course here is Fundamentals of Mathematics. It's a course that I would certainly recommend to you. But basically what Fundamentals of Mathematics does is it tries to reduce everything to the barest set of axioms possible, and well, that axiomatic set is then to be considered natural or not, but it's a set of axioms that mathematics is built on. And within that set theory, we can formally define what the numbers are, and we basically define set theoretical entities that act exactly like numbers should. But that definition really isn't something that you want to work with on a daily basis because it is rather complicated. And so rather than trying to define numbers, what we are considering here is their representation, right? It's the 5 cows, the 3 cowboys, and all that. And so we will assume that we know what a number is, or that we think we know what a number is, and we will discuss the meaning of the common representations in base 10, base 2, and base 16. Once we've done that, we'll focus on the algorithms that are used to carry out the regular arithmetic operations and how they are realized in computers, because that ultimately tells us how expensive or not these operations are. So, the definition for the base representation, that actually looks a whole lot more complicated than what we think it should be, but if you take r to be a number that is a natural number but not 1, and that'll be our base, and we let digits dn minus 1 through d0 be numbers between 0 and r minus 1, then we can define dn minus 1 through d0 in base r representation to be the sum j equals 0 to n minus 1 dj r to the j. So the j's digit counts as is multiplied with the j's power of the base. So as an example, if you take the number 8,675,309, well, that's 8 times 10 to the 6th, 8 million, plus 6 times 10 to the 5th, 600,000, plus 7 times 10 to the 4th, 70,000, plus 5 times 10 cubed, 5,000, plus 3 times 10 squared, 300, plus 0 times 10 plus 9. And yeah, that's it. And then that's, of course, the kind of stuff that, again, we've learned in elementary school. This is the ones digit, this is the tens digit, the hundreds digit, the thousands digit, and so on, and so on, and so on. And yes, this really is the formal realization of that digit representation, right? And the thing now is that there are other bases, and one of the very common bases is the base 16 for hexadecimal numbers, as they are called. Well, first of all, you have to think about what the digits are in base 16. You use 0 through 9. What do you use for 10? Well, for 10 you use A. For 11 you use B, for 12 you use C, for 13 you use D, for 14 you use E, and for 15 you use F. And so that means that this number now actually makes sense. The number 3A4F can then be converted to base 10 notation. And all of a sudden we see that that definition can help quite a bit, right? Because 3A4F, we know that that is 3 times 16 cubed plus 10 times 16 squared plus 4 times 16 plus 15. And no, I'm not going to work that out in my head. That's something. It ends up being 14,927. And I'm pretty sure I used a computer for that. If now, on the other hand, we want to convert the base 10 number 45,788 to base 16, well, how on earth are we going to do that? Well, basically, if you're looking at the base representation, and if you divide the number by the base, then the least significant digit, the rightmost digit, is the remainder that you get if you divide the number by the base, right? If you're looking at 45,788, if you divide that by 10, you get a quotient of 4578 and a remainder of 8. If you divide that quotient by 10, you get a quotient of 457, 457, and a remainder of 8. If you divide 457 by 10, you get 45, a remainder with a remainder of 7, and so on and so on. So apparently repeated division spits out the digits in a right to left fashion, and that should also work when we use base 16. So 45,788, if you work that out, that's 2,861 times 16 plus 12, and you can verify that by doing the division. And so that means that the rightmost digit is a C. 2,861 is 178 times 16 plus 13, so the next digit is a D. 178, now that's when we can actually verify, right? Because 11 times 16 is 176 plus 2 is 178, so that really does work, and that means that the next digit is a 2. And 11 is 0 times 16 plus 11, so the next digit is a B. And that means that the base 10, the base 16 conversion of this number is B2DC, like it's written here. And that would be 11 times 16 cubed plus 2 times 16 squared plus 13 times 16 plus 12, which you can work out to be really 45,788. Okay, so how does that work in general? The theorem is that the place value in base R is worked out as follows. If you take R to be a natural number not equal to 1, and that's fixed, and you use D to be a natural number, then you define Dn and Qn as follows. For n equals 0, you let Q0 and D0 be the quotient and remainder of the division of D by R, just like we did previously, right? We divided by the base, and then we kept that quotient and continued with that. And so now recursively, once you have Qn defined, you let Qn plus 1 and Dn plus 1 be the quotient and the remainder of the division of Qn by R. And that was just what we did, right? We kept taking the quotient and dividing it by R. And that means, in this theorem now guarantees that then for all natural numbers, so that R to the n is greater than D, we have that Dn is equal to 0. And if n sub D is a natural number or 0, and it's the smallest number, so that for all n greater than nd, we have that Dn is equal to 0, then D is just the sum n equals 0 to nd dn R to the n, which means that the dn's are the base R representation in digits. D stands for digits all the way through here, of the number D. And so now, well, now we have to prove that. Well, first we should note that for every D, a number in D, as we specified, must exist, because after all, this process defines natural numbers Q sub n, so that Q sub n plus 1 is always smaller than Q sub n, because we always get the Q sub n plus 1 by dividing the Q sub n by D, so that defines shrinking natural numbers, and we know that no sequence of natural numbers can decrease indefinitely. So at some point in time, after so and so many divisions, you will have that the next Q is 0, and that terminates your sequence, right? Okay, so now we continue. And the proof is an induction on n sub D, because now we know that for every D there is such a number n sub D, we're going to use it. So the base step for n sub D equals 0 is trivial. because if this terminates after the first step, that means that your number is between 0 and r minus 1. And that, of course, means that with q sub 0 equals 0 and d sub 0 equals d, the equation holds and we're done. So now we take the induction step n to n plus 1. So we assume that the result holds for n sub k equals n. And we let d be so that n sub d is capital N plus 1. So we're going to the next number here, to the next number of divisions necessary. Okay, so then there are q sub 0 in n union 0 and d sub 0 in 0 through r minus 1. So that our number is just q sub 0 times r plus d sub 0. That's just the regular division algorithm again. And now we know, however, if it takes n steps to n repeated divisions by r to get rid of the d, then it will take one less such division to get rid of the q sub 0. And that means for q sub 0, we have nq sub 0 is capital N, and that means we can apply the induction hypothesis. And so that means that now the number, and moreover, the numbers that are generated by the procedure applied to q0 are the digits d1 through d sub n plus 1 for d. And so that means that d is equal to q0r plus d0, and that'll be the sum n equals 1 to n plus 1 dn times r to the n times r plus d0, and that is just the sum n equals 0 to n plus 1 dn r to the n, and that's what we wanted to have there. Okay, so now what do we do with addition and subtraction? Well, if we have two numbers a and b, whose base r representation has n places, then I claim it takes 2n minus 1 additions of digits to compute the base r representation of a plus b. Alright, the proof, well, the proof is really just the regular addition algorithm. You take the representations to be an minus 1 to a0, right? If we have n places, then the nth place has an index n minus 1, because we always start counting at 0, because we want to have that this has value r to the 0th. And so we've got these two sequences of digits. And then we add, and so a plus b is this digit sequence plus this digit sequence. We know that the first one is the sum I equals 0 to n minus 1 air to the I. We know that the second one is the sum j equals 0 to n minus 1 bjr to the j. And so that means when we add them up, we get the sum j equals 0 to n minus 1 aj plus bj r to the j. And well, now we've got a small problem here, and that is sum of the aj plus bj could exceed r minus 1. So we could have carryovers, as we also know from the addition algorithm that we have learned in school, and we have to take care of those. But what we do know is that there are a c1 that is either 0 or 1, and a d0 that is between 0 and r minus 1, so that a0 plus b0 is c1r plus d0, and now c1, that's the first carryover here, right? So that's the first carryover. That's why I call that thing c. And so now I can go recursively. And for every j from 1 to n minus 1, we've got a carryover cj plus 1 that is either 0 or 1, so that dj and a dj between 0 and r minus 1, so that aj plus bj plus cj is cj plus 1r plus dj. Now, you may need to think about here how big that carryover can be. But because we're going in steps of size r, it can never exceed a full value of the base, and we're only adding two numbers here, right? I'm currently thinking of, well, I had bigger carryovers when I did my taxes and things like that, but that's because I was adding more than two numbers. When you add just two numbers, then your carryover will always be either a 0 or a 1. And so the representation of a plus b then is a plus b, which is last carryover and then all the digits that you have computed all the way through. And that takes 2n minus 1 plus 1 additions of digits to obtain, because the 0th place we do just one addition, but then for all the places from 1 through n minus 1, we do 2 additions. So that gives you 1 addition from here and 2 n minus 1 additions from there. And that should be the theorem. Yes, that's it. Okay, so in binary, that would work like this. If you take the number 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, and you add to it 0, 0, 1, 0, 1, 1, 1, 0, well, 0 plus 0 is 0, 1 plus 1 is 0 with a carryover of 1, 1 plus 1 is 0 with a carryover of 1, 1 plus 1 plus 1 is 1 with a carryover of 1, 1 plus 0 is 1, 1 plus 1 is 0 with a carryover of 1, 1 plus 1 is 0 with a carryover of 1, and then we have 1 plus 0, and that's another 1 here. Okay, I think we're now looking at subtraction, and if you've got two natural numbers whose base R representation has n places, and so that a is greater than b, then I claim it takes 2n minus 1 subtractions of digits to compute the base R representation of a minus b. How does that go? Well, we take the representations just as before, and then a minus b is the sequence of digits minus the other sequence of digits. So that's sum I equals 0 n minus 1 ai r to the I minus sum j equals 0 to n minus 1 bj r to the j. And of course you can combine that, so that's the sum j equals 1, j equals 0 to n minus 1 aj minus bj r to the j, and we've got the same but that we had for addition, but, so namely we say, but sum of the aj minus bj may be negative, and so that's where we need to carry over in the other direction. And so we know that there are C1 between 0 and 1 and D0 between 0 and R minus 1, so that A0 minus B0 is negative C1R plus D0. And so recursively now, for each J between 1 and n minus 1, there are Cj plus 1 being 0 or 1, and Dj between 0 and R minus 1, so that Aj minus Bj minus Cj is negative Cj plus 1R plus Dj, and the representation is Dn minus 1 through D0R in base R, and that is because we are assuming that A is greater than B, so ultimately all those negative signs don't get through to the final digit there. And well, it takes 2n minus 1 plus 1 subtractions of digits to do that, because we need one subtraction to start things out, and then for all the other places we need potentially two subtractions. And of course you could say here that, well, if we have a 0 we don't really do a subtraction, but we need to think of this in terms of how this would be implemented in a computer, and before you ask a computer to check whether something is 0 or not, especially if it's individual digits, it's just a lot faster to just do the subtraction. Okay, so example in binary, well, if I take 1, 0, 1, 0 minus 0, 1, 1, 1, well, what do I get? I get 0 minus 1, that would give me a 1 with a negative carryover, right? So then I've got 1 minus 2, which gives me a 1 with a negative carryover. Then I get a 0 minus a 2, which gives me a 0 with a negative carryover, and then 1 minus 0 here gives me a 0. And that should also be correct, because let's see. This one is valued 1, 2, 4, 8, so 8 plus 2 is 10, and we subtract off of it 4 plus 2 plus 1, 10 minus 7, and that's 2 plus 1, which is 3. Yeah, that would still be correct here. Multiplication, okay, now it gets a bit hairier, because what do we know? I mean, we know from school multiplication takes longer than addition and subtraction, because multiplication is essentially repeated addition, and that's also going to carry through here. So the first thing we're going to do here is to just see how we can break the customary algorithm up. And if you take the product of the number with base R representation being given by these digits here with R to the m, then that is the number with base R representation being the same digits, only with m zeros stuck into the back. Think of what we do when we multiply with 100. All we do is we attach 2 zeros at the end, right? And that is the kind of thing that we need to do in the regular multiplication algorithm when we work out what happens when we multiply with the hundredths digit, right? That's where we're doing a left shift by 2 digits and then do the multiplication with the hundredths digit. So this theorem basically encodes this very familiar idea. And so what's the proof? It ought to be pretty simple. If you take R to the m times the number that is represented by these digits, That's of course r to the m times the sum j equals 0 to n minus 1 xj r to the j. Now I can multiply r to the m in there. So we get sum j equals 0 to n minus 1 xj r to the j plus m. And this is a sum where I can shift the index. I can say k equals j plus m. That gives me an r to the k. If k is j plus m, then j is k minus m. And if k is j plus m, well, then when j is 0, k is m. And when j is n minus 1, then k is m plus n minus 1. And then, of course, I can add a 0 to that, sum k equals 0 to m minus 1, 0 times r to the k. And that's exactly the digit representation of what I have here, which was the claimed result. And so that wasn't so bad. But of course, the hard part in multiplication isn't the shifting. The hard part in multiplication is the multiplications by digits. And so the usual multiplication of two in-place numbers in base r, I claim, requires n squared multiplications of digits, 5n squared minus 6n plus 1 additions of digits, and n minus 1 shifts. Okay, how does that go? We first consider multiplication with one digit, because shifting will take care of a lot of other stuff, right? So if I take d to be a digit between 0 and r minus 1, then d times the base r representation of my number b is just sum j equals 0 to n minus 1 d times the bj r to the j, which is sum j equals 0 to n minus 1 dbj r to the j. And of course, again, we have to say, but sum of the dbj could exceed r minus 1. We know, again, that there is a carryover, and that carryover now can be between 0 and d minus 1. And the remainder, which could be a number between 0 and r minus 1, so that d times b0 is c1r plus e0. My phone rings, so we'll take a break. And we're back. Okay, now in this one we want to be really careful, but basically what we have here is we have two numbers that are both smaller than r minus 1, and if you multiply those two together you can get at most r minus 1 squared. And if you then factor out an r, you realize that actually your c can be at most 1 less than one of the factors there. And then the remainder, of course, is still r minus 1. And yeah, then we continue. And so recursively, that means that for each j, we have that there is a cj plus 1 between 0 and d, and an ej that is a remainder, so that dbj plus cj is just cj plus 1r plus ej, because what we're now doing is, of course, we're taking the digit plus the carryover, and now the carryover could give us up to another wraparound. We could pick up an extra r, so that the cj plus 1 could actually be up to d. And then the remainder, of course, is just an ej. And the representation of db is that we're going from en all the way through e0 in this situation, where we just carry out all n steps of the algorithm. So as before, the remainders are the digits, and everything else is just piling up and providing further digits as we go through that. And that took n multiplications, because at the 0 step we multiply, but then also at every further step we multiply d times bj. And it takes n minus 1 additions of digits to obtain, because, well, first time around we don't add, but then all the future times we have to add the carryover. And if we now conclude this proof, if I take a times b, well, that is these digit representations multiplied with each other, so that's the sum j equals 0 to n minus 1 of the aj digit times the digit representation of b times r to the j. And so that is a sum of n numbers with n plus 1 digits each, right? And that is, well, they actually only have n digits, but if it has n digits, then it certainly, we could also pretend it has n plus 1 digits. I think that should just be an n here. And the jth number takes in multiplication of digits, in minus 1 additions of digits, and 1 shift to reduce, and that is because, of course, the shift by 1 bit, actually, or by 1 digit would always be accomplished by just reusing the previously shifted number if we store that in between. And so that means we need n squared multiplications, n times n minus 1 additions of digits, and n minus 1 shifts. And after that, we add the numbers up, and assuming that the result has 2 n places, that will take n minus 1 times 4n minus 1 additions of digits, and so that would be 4n squared plus 5n plus 1 additions of digits. And if we include the earlier n times n minus 1 additions of digits, we obtain a total of 5n squared minus 6n plus 1 additions of digits. And yeah, I'm currently having my doubts again about the n plus 1 here, so maybe the theorem actually is an overestimate. We're actually going to see, once we talk about complexity, that an overestimate is just fine. And so what we have here ultimately, however, is that it takes a quadratic number of operations, and that's really what we're going to have to worry about when we talk about larger scale complexity. As an example in binary, well, if you take the number 1011 and multiply it with 10, okay, take the number 1001 and you multiply it with 1011, well, then, of course, 1 times 1001 is 1001. Then you multiply 1 times 1001 in the next place, so it's just the regular shift that we also know from the regular multiplication algorithm in base 10. This one, of course, gives us just a bunch of zeros, and then 1 times 1001 gives us 1001 again. And now if we add this up, well, we get 1, 1, 0. 1 plus 1 is 0 with a carryover of 1. 1 plus 1 is 0 with a carryover of 1. 1 plus 0 is 1, and 1 plus nothing is 1. So this is the same algorithm as we do in base 10, only that in base R it feels a little bit unfamiliar. So what would be more natural than that the division algorithm also has its usual analog for any base, and the usual division of a natural number a in base R by another natural number b smaller than R requires a number of operations that depends on the number of digits of the quotient. That is as far as I'm going to go with this theorem. The counting really gets complicated, and ultimately what we're going to realize is it takes n squared operations where n is the number of digits, and that's really what we need for the complexity analysis. So how would we work this out? Well, your quotient is a representation qn minus 1 through q0 in base R. And, yeah. Right, it is the quotient, sure. And so that means that if you take a and divide it by b, then a is bq plus r. I'm starting here with something that is actually a derived quantity, but yeah, you can do that, right? So q is the quotient. And so you have a equals b times quotient plus r is the remainder. And of course, that is b times the sum j equals 0 to n minus 1 qj r to the j, because that was the representation of the quotient, plus the r being the remainder again, where 0 is less than or equal than capital R is less than b, because r is the remainder in the division by b, right? This is the division of a by b. Well, then we have that a minus the highest, minus b times the highest order digit in the quotient times r to the n minus 1 is just b times the same sum as before, only up to n minus 2, q to the j, q sub j r to the j, plus the remainder. And that means to divide a by b, we can proceed as follows. We first find the unique n, so that a minus b times r to the n minus 1 is greater than 0, and a minus b times r to the n is smaller than 0. And so now qn minus 1 is the largest digit between 0 and r minus 1, so that a minus b times qn minus 1 r to the n minus 1 is greater or equal than 0, and a minus b times qn minus 1 plus 1 r to the n minus 1 is smaller than 0. Now that Sounds really, really complicated, but that is exactly what we're doing in the regular division algorithm when we figure out how many times the divisor, the b, goes into the number that we are dividing by, how often it goes into the numerator. Because the r to the n minus 1 is the shift, the b is of course what we're multiplying with, that's our divisor, and we're saying, well, say 5 times still goes in and 6 times doesn't go in anymore. So that's the number that we would be recording there. And then you said r sub n minus 1, the next remainder, to be a minus b times q n minus 1 r to the n minus 1. That is exactly the subtraction that we're doing in the division algorithm. And now we act recursively. We said j equals n minus 2. And now we continue, because if now we have our rj, then we let qj to be the largest digit between 0 and r minus 1, so that rj minus b times qj times r to the j is greater or equal than 0, and so that rj minus b times qj plus 1, r to the j is smaller than 0. So we continue to do exactly this thing that we do in the division algorithm. How often does my denominator go into a certain part of the numerator that is shifted the right way? And you said rj minus 1 to be rj minus b times qj r to the j. That's what we always subtract off. And you decrease j by 1. And when j is equal to negative 1, you set r to be r minus 1, the last remainder, and you stop. And otherwise, you just keep repeating this loop until j is r minus 1. So that means that now, because rj is b times qj r to the j plus rj minus 1 for all rj, we can now show that this really gives the right result, because we have that a is b q n minus 1 r to n minus 1 plus r sub n minus 1, which is keep the front, and rn minus 1 is b q n minus 2 r to the n minus 2 plus rn minus 2, and now you can also express rn minus 2, and you keep doing that until you've got the sum bq n minus 1 r to the n minus 1 bq n minus 2 r to n minus 2 plus all the way to bq1r plus bq0r plus r, which was the r sub negative 1, right? And because we have a step, okay, so now first of all, that shows that this is the right result, because we started with q satisfying exactly this equation here. And now because we have a step for every place in q, we obtain that the number of steps really depends on the number of places that the quotient has here. Okay. So if we now go back and implement that, of course, it's the usual division algorithm. So we just look at the divisions that we already have looked at once before. We divide 7,547 by 23, and because that animation takes a while to set up, I just use the same numbers. But it's the same thing, right? We take the 23, and we know that this is 300 times 23 still goes into the whole thing, because now this 69 is 3, which is the digit of the quotient, times the 23, times the power of the base, which is r squared here, which is 10 squared. And so then we subtract, as we did before, and of course we keep 247, if you will. We pull down just the 4, and now we realize that 1 times 23 goes into 24, and so now this is basically 1, the digit of the quotient, times the denominator times 10, which is the appropriate power of the base. We subtract, we end up with a 17. 23 doesn't go into 17, and we end up with a remainder of 17. And so the quotient is 310, the remainder is 17, which is this multiplication here. And we can see again that basically the shifts are the zeros that we have dropped here, and the algorithm is only looking as if we're playing with digits, because we're deleting a few things that are inessential from the more abstract version that we have just seen in the theorem. Okay, now we're going to talk about complexity, and basically when we talk about how long an algorithm runs on input size n, eventually only the fastest growing term in the estimate matters. So we want to have a way to express runtime, and which is of course a major aspect of complexity, that focuses on the essential part of the estimate. And to do that, we use what is called big O notation. If you've got two functions defined on the natural numbers that take positive values, and if there is a k so that for all sufficiently large x, so that just means it's got to happen eventually, but it may not happen until x is greater than 50,000 trillion or something like that. But so for sufficiently large x, we have f of x being smaller or equal k times g of x. Then we can also write that f is capital O of g. Basically, f grows on the order or slower of g. And so what that means is, for example, when you've got 5x cubed plus 2x squared plus minus 132x plus 4, that's capital O of x cubed. Because in the long run, when x becomes 1,000, when x becomes 10,000, and so on, the only term here that really matters is the 5x cubed that will have the largest contribution. All the other terms will certainly still contribute, but the contribution will be small compared to the 5x cubed. And that's, yeah, it's because 5x cubed plus 2x squared minus 132x plus 4 is smaller or equal than 6x cubed for large x. So that's how we connect it to the formal definition. As a theorem, then, we can see that this capital O notation allows us to circumvent a few computations that we would otherwise have to do exactly, such as if f is capital O of g and I multiply it with a number, then c times f is also capital O of g. And that's because if we have that for sufficiently large x, f of x is smaller or equal than k times g of x, well then, for those same sufficiently large x, for all sufficiently large x, we have that c times f of x is smaller or equal than c times k g of x, and so now instead of k we use c times k, but that is just the same because all we need is that the function on the left is less than or equal than some constant times the function on the right, and we've got that here. If f1 is capital O of g and f2 is capital O of g, well then f1 plus f2 is also capital O of g, and that's because if for all sufficiently large x we have that f1 of x is less than or equal than k1g of x and f2 is less than or equal than k2g of x, well then for all sufficiently large x we have that f1 plus f2 of x is f1 of x plus f2 of x. Well, that's rather boring. That's less than or equal than k1g of x plus k2g of x, coming from the hypothesis here, and that's of course k1 plus k2, which is some number times g of x, and so that also satisfies the definition of this left-hand side being capital O of g. And finally, I think we're going to talk about multiplication also. So if f is O of g1 and f1 is O of g1 and f2 is O of g2, then the product is O of g1 times g2, and it's the same story. If f is bounded by k1 g1 and f1 is bounded by that and f2 is bounded by k2 g2, then the product will be bounded is f1 of x times f2 of x for all sufficiently large x that is bounded by k1 g of x plus times k2 g2 of x, and that's just a number, namely k1 k2 times g1 g2 of x, and so that means that f1 f2 is bounded by, for sufficiently large x, bounded by k1 k2 times g1 g2, and so that means that it's capital O of g1 g2. So that means that subtraction and addition of two n-bit integers takes capital O of n steps. Conventional multiplication of two n-bit integers takes capital O of n squared steps, so that's where, even if I was a little insecure near the end of my proof there, where I just said, okay, yeah, it's an upper bound, that's because ultimately it's all capital O of n squared, and that's really what we're going to worry about for complexity. And conventional division of a 2n-bit integer by an n-bit integer, that'll take O of n squared steps because we have to do these trial multiplications there. Okay, proof is that we just take all these earlier results and translate them into big O language. You have to count very carefully for division because we haven't really worked out the exact situation there. And of course I'm taking a sidestep there, but I also have to leave something for you to cut your teeth on, and so that's what I left there. Okay, so the upshot is that conventional multiplication and division are much more expensive than addition and subtraction, and so that means, also as a side note, it certainly is sensible to still count bit operations even when computers work on bytes, words, double words, and so on, because what happens is when a computer, as it should, works with several bits at once, that divides the effort by a factor of up to 8 byte, or for 16 if you want to work with words, or 32 if you work with double words, which certainly is significant. I've implemented certain search algorithms for my research in what is called bit parallel fashion, and trust me, the bit parallel fashion, if that cuts your execution time by a factor of 32 or something like that, that is just great, right? That is huge from an implementation point of view. But from a theoretical point of view, it only changes that constant factor in front of the O, and that means, considering here that we are looking from a theoretical point of view as something that we can make as big as possible, well then, if we can, for example, cut down our execution time by a factor of 32, if my algorithm takes O of n squared, then maybe I can stick an extra digit in there now, but that's about it. So we're not really getting that much in the long run, and typically we probably won't even get that well, yeah, we're probably going to get an extra digit or so, but that is ultimately not that big if we're looking at something where we want to work with 100-digit numbers. Well, 101-digit numbers, they're really not that much different from an everyday point of view than 100-digit numbers. Okay, so now that also means that we will be interested in faster algorithms, and there is a faster algorithm for multiplication, and so we're going to give a bit of an overview here. So here's a lemma that at first sounds really strange, because it says if there is a multiplication algorithm for two n-bit integers that takes m of n bit operations, so we just take multiplication of n bit operations, then this lemma says that there is a multiplication algorithm for two 2n-bit integers, so we double number of digits, that takes at most 3 times m of n plus c times n bit operations, where c is a constant. And so basically what that means is that as you double your number of digits, you triple your effort. But remember that in the conventional algorithm, you would, as you double your number of digits, you would have an effort for a 2n quantity squared, so you would quadruple your effort. So that is something that ultimately will help reduce the effort, because now when we double the number of digits, we only triple our effort rather than having to quadruple it. Okay, so, well, what do? We take the bit representations, and we consider the numbers that are obtained by splitting the bit operations, right? We take the top n digits of A and call that A1. We take the bottom n digits of A and call that A0, and we do the same thing with B and call that B1 and B0. Well, then A times B is 2 to the n A1 plus A0 times 2 to the n B1 plus B0, and we can multiply that out, and of course that requires 4 operations, right? Because it's 2 to the n times 2 to the n to the 2n times A1 times B1 plus, and then we have 2 to the n A1 A0, well, okay, 2 to the n A0 B1, 2 to the n A1 B0, and A0 B0 here. So that requires 4 multiplication, but so now we're hoping that somehow we can combine stuff so we can get away with less. And basically what we notice is that A0 B1 and A1 B0 also occur when you multiply A1 plus A0 with B1 plus B0, and also when you multiply the difference. And so what we would still need is we would not need terms A1 B1 and A0 B0, and we don't want to take them from here because we need them multiplied with a 2 to the n. Okay, so what are we doing here? We keep the first term, we add 2 to the n A1 B1, we subtract it again so we don't change anything. Then we have the 2 to the n A0 B1, the 2 to the n A1 B0, and then we want to subtract 2 to the n A0 B0, and we're going to add it back in because we cannot change the problem, and then we have the plus A0 B0 from the end. So all we have done is we've used that one trick that there is in working with elementary mathematics and with numbers. We've added 0, and we've done that twice. But now we can combine that differently, right? Because now this is 2 times 2 to the n plus 2 to the n A1 B1 from here. Then we have 2 to the n times negative A1 B1 plus A0 B1 plus A1 B0 minus A0 B0 plus 2 to the n plus 1 times a0, b0. And that, of course, is 2 to the 2n a1, b1 plus 2 to the n a1, b1 plus 2 to the n. And here, this is now a1 minus a0, b0 minus b1. That's one of those factoring things. And personally, I would just go ahead and multiply that out to double check. a1 minus b1 is here. a1 b0 is here. Negative a0 b0 is here. And negative a0 negative b1 is plus a0 b1, which is here. So that is the right factorization. Then we've got a 2 to the n a0 b0 and an a0 b0 here. And of course that looks like it's more multiplication, but we only multiply a1 with b1, and once we've got that number we can store it, of course. We multiply e0 with b0, and if we need to use that twice we just use one that is stored. And we've got a1 minus a0, b0 minus b1, and that's of course then just one multiplication. Also, subtractions, as people say, are cheap, and if we multiply with powers of 2, those are just bit shifts, and bit shifts are cheap also. So that means basically the product takes 3 multiplications, and then if you count it all the way through, it requires 4 shifts, and shifts are cheap, and it also requires 4 additions, which are cheap, and it requires 2 subtractions. And so that means we have 3 times the complexity of what the multiplication of the smaller numbers takes, and then we have 4 plus 4 plus 2, which is 10 times a constant number of steps, and so that's how we would choose that C that was mentioned in the theorem. Okay, so what does that tell us? That tells us now that there is a multiplication for 2 n-bit integers that takes O of n to the log 2 of 3 steps, and of course log 2 of 3 is smaller than 2, which is nice. And well, let's just go through the proof, because this is now just a little bit of algebra here. Because basically, by adding zeros up to the next power of 2, we can assume without loss of generality that the number of digits is a 2 to the k. And because typically that happens anyway, because when a computer works with a 64-bit number, if that number sits in the lowest three bits, the other leading bits are still leading zeros and the operations are being carried out anyway. So filling up with leading zeros is not a problem here, it's actually quite realistic. Then let m of n be an upper bound on the number of steps for the multiplication of 2 n-bit integers, right? That's that mysterious m of n that we had before. Then we will prove that m of n is m of, which is m of 2 to the k, is smaller or equal than some number a times 3 to the k minus 2 to the k, where a is a constant that will be greater than or equal to than that c from the previous lemma. Okay, and this upper bound, of course, is capital O of 3 to the k, which is equal to capital O of 2 to the log 2 of 3k, and then, of course, 2 to the k is n, so this is capital O of log 2 n to the log 2 of 3, which is exactly what we claimed there. Okay, so that would establish the theorem. So the proof of the upper bound, however, now is an induction on k, and because we're interested in the asymptotic estimate, the base step for k is actually quite trivial, because for k equals 1, we're looking at m of 2, and all we have to do is we realize that the multiplication takes a constant number of steps, and so we just need to make the a large enough. And as we conclude the proof now, the induction step will be if your number of digits is 2 to the k plus 1, then that's 2 times 2 to the k. And by the preceding lemma, we know that there is an algorithm that multiplies 2 to the k plus 1 bit integers in 3 times m of 2 to the k plus c times 2 to the k steps. And by induction hypothesis, that now means that m of 2 to the k plus the number of multiplications for multiplying 2 to the k plus 1 bit integers is 3 times the number of multiplications for the 2 to the k bit integers plus c times 2 to the k. We know that by induction hypothesis, this m here is bounded by 3a times, this 3m is bounded by 3a times 3 to the k minus 2 to the k, and we still have the plus c times 2 to the k. And now it's algebra. We have 3a 3 to the k minus 3a 2 to the k plus c 2 to the k, and that's 3a 3 to the k plus minus 2a 2 to the k. Yeah, I'm splitting up the 3 into 2 plus 1 plus c minus a to the k. And that's a times 3 to the k plus 1 minus a times 2 to the k plus 1, because we want the a to be greater than that c. So if we just subtract something off here and drop something that is subtracted, things just get bigger. And that is a times 3 to the k plus 1 minus 2 to the k plus 1, and that's it. Okay, so even though this estimate is asymptotic, let's just do a quick estimate to see that that algorithm from this preceding theorem already helps for a small number of bits. The elementary algorithm takes at least 5 n² bit operations, and in fact it takes more than that. So, and we also see that this algorithm takes at most 16 n to the 1.59, which is what log 3 to base 2 is. That many bit operations, and in fact it takes fewer because the induction did also a subtraction, right? And so for a 64-bit integers, 5 times 64 squared is 20,480, and 16 times 64 to the 1.59 is 11,912. And now realize that the 11,912 is actually an overshoot because we dropped the subtraction in the theorem, and the 20,480 is an undershoot because I didn't take into account the other terms that we had in the elementary operation. And that means that the algorithm from the preceding theorem is a speed up by at least a factor 2. And of course, again, even though ultimately it's just a constant factor, you don't want to give constant factors away if you can set up a faster algorithm, right? So independent of how fast your chips are, that is an improvement that must be implemented. Everybody would be extremely mad with an operating system designer if they just use a terrible algorithm and we use a supercomputer at half the speed that it could run just because some programmer didn't put the right algorithm in there, right? That is just something that does not happen and should not happen. For precise cost-benefit analysis, of course, you need to take into account which bit operations can be performed simultaneously on your computer, because at some point in time, the splitting really is overtaken by the fact that you can do simultaneous bit operations. But what that would then mean is that you would just hardwire huge a huge number of bits for your integers. Say you go with, I don't know, 1024-bit integers or something like that, and then split that down with an algorithm like that until you've got 64-bit integers where things go more rapidly, or maybe 32-bit integers, and you use a fast algorithm on that. Alright, so, and yeah, that's because additions don't go bit by bit, but byte by byte, word by word, or double word by double word, and you've got to take that into account. And it always ultimately depends on your bus width in your processors, which with current operating systems, at least on PCs, it's 64 bits, and I mean, that's also the processors that people use in supercomputers. Okay, but anything that speeds up the elementary algorithm, as I said, should similarly speed up an algorithm on a bigger machine. And yeah, I always tell these war stories about that I've read the operating system of the Commodore 64. I am really not sure how the Commodore 64 did it. My memory is terribly hazy on that right now. And I'm also not sure how dedicated floating point units work, because for FPUs, I'm quite certain they don't use the conventional algorithm, I can tell you that. But there are more algorithms around. So for example, and here's where things become, I think, a little bit of trying to look at the future or trying to look at alternatives. With fast enough storage, you could use that a times b is nothing but a plus b divided by 2 squared minus a minus b divided by 2 quantity squared. First of all, let's make sure that that works out. Yeah, because what you have here is you get a squared over 4 and b squared over 4, and you subtract it in both cases, and the mixed terms are 2a over 2b over 2, so you get ab over 2 here as a plus, and you get it as a minus minus here, and so that would really add up to ab. And well, that takes 2 subtractions, 1 addition, and 2 shifts, because divisions can be obtained in binary arithmetic. A division by 2 is nothing but a right shift. and 2 lookups of squares. And now you could rightly say, well, how do you look up those squares? Well, that approach could be used on 16-bit pieces of larger numbers, because if you're looking at 16-bit numbers, 2 to the 16, oh goodness gracious, I was always so proud that I knew my 16, my powers of 2. 2 to the 16 ought to be 65,536, because that's the number of bytes that the Commodore 64 had, and that was 2 to the 16 bytes. So that was just a number that I pulled out of a different part of my brain here. But so that would mean you would need something like storing 66,000 square numbers, and that by now is an array that actually doesn't feel that big anymore. However, you've got to be careful, because you'd have to keep that array in RAM, so you don't have to go to hard drives, and you have to keep it in a place where it's rapidly accessible. So maybe it would only work on 8-bit pieces or so, but it certainly is something that is, I think, somewhere in the running where somebody ultimately might realize, hey, here's another way in which we can speed up floating point multiplications. There actually is an algorithm that is of the order O of n times log 2 of n times log 2 of log 2 of n, and I am not sure what that algorithm looks like. I think it's terribly complicated, and it may even be that that algorithm, even though it is fast in theory, isn't quite practical, and that sometimes also happens. I know that certainly is the case for an algorithm for matrix multiplication, and that is because that other algorithm I'm thinking about has a huge C out front here, and of course for small sizes, and some point in time when you look at 10 to the, I don't know, if you look at 10 to the 100, then all of a sudden 10 to the 50 is a small size, but if you've got a huge C of 10 to the 200 out front, then the small size 10 to the 50 really already is affected by that constant, even though that constant ultimately is something that is better than having something that runs on n squared. So the upshot that we can take away from this is that this becomes very, very complicated. We just have to be careful. It is also apparently true that there is a capital O of m of n division algorithm for a 2n-bit integer divided by an n-bit integer. So there are certain kinds of fast division algorithms out there. So this now really already goes to what probably is the frontier, and it's fairly elementary, right? All we're doing is we're multiplying numbers. There's something that is quite primitive about it, but at the same time, anybody who can come up with a faster way to multiply numbers, with a faster way to divide numbers, is somebody who makes a significant contribution to supercomputing, because all of a sudden these algorithms, once they are verified and tested and everything, could become part of operating systems, and all of a sudden certain huge computations run 10% faster, 15% faster, 20% faster, which is something that from a development point of view is huge. Theorists will still say, well, you still haven't knocked it down from n squared or n times log n or whatever we have otherwise, but at the same time it is something that is certainly relevant as an application. I'm not holding my breath that there are too many more improvements in these algorithms, because you can imagine that an awful lot of very smart people who certainly know how to multiply numbers have looked at these things. However, I'm also not aware if there are any kinds of proofs that certain algorithms are optimal. This one here might have something that says things just can't get any better than that, but I would not bet money on that right now, and that's because I am just not doing research in that area. So this is something, if necessary, look it up for yourself. I'm good and tired because we've certainly done a lot of stuff here. You may be too, so take a break and then hit the homework. I'll see you in the next one.